then we can continue by necessary conditions for extreme values. For functions of two variables here we will talk about. So fxy is a function of two variables, as you can see, and it can have local or absolute extreme value at a point AB on its domain if and only if AB is one of the followings. So it can be where the critical point is, so where the discriminant is 0, where the singular point is, so where AB is the singular point, and also it can be a boundary point of the domain of our function. So those are the, if you remember, those are for non-variable functions. So the absolute extreme values or extreme values, you can say in general, can appear only on those points. If we talk about the or remind the bounded function set, a set in R over n-dimensional space is bounded if it is contained inside some ball where x squared plus x2 x1 squared plus x2 squared plus xn squared smaller or equal to r squared of finite radius r. So this is the definition that we have seen on topological definitions. So any set on n-dimensional space is called bounded if it is contained inside that ball in n-dimensional space. Sufficient conditions for extreme values, we will see that definition. So if f is continuous function on n variables whose domain is a closed and bounded set. So those are the conditions of domain in Rn. Then the range of f is bounded set, of course, and it will be of real numbers, and there are points in its domain where f takes an absolute maximum and minimum values. So if you remember that theorem for non-variable functions, it is the same. It is just the generalization in n-dimensional or functions of n variables, let's say. And here the sufficient condition is f is continuous function and domain of f is closed and bounded set in Rn. So those are the sufficient conditions. Then that means if you have those conditions, then it is sure you can directly say f takes an absolute and let's say directly absolute extreme values. And let's see. Is the paraboloid x squared plus y squared, and if we compute the gradient of f, it will be f1 fxy times I plus f2 fxy times j. So the gradient vector has components 2x and 2y, and we will try to see where the gradient is 0. So as you can directly say, at point 0, 0, the gradient is equal to 0. So that will be 0. So that means the point 0, 0 is the critical point of our function x squared plus y squared, the paraboloid. And for all the points, also let's say where the function is defined, x squared plus y squared is defined for all points on xy plane, right? So for all xy in R square, then fxy is defined. So for the rest of the points, which are non-zero points of the domain, since the function is defined as x squared plus y squared, so those two values will be always positive because you have the power 2 for both. Then for all non-zero points on xy plane, fxy will be always positively defined. Okay, so that means from the definition of absolute minimum value, f has the absolute minimum value 0 at 0, 0 at point or at the origin, you can directly say. And also for the second graph that we have seen, I will show that those again. gxy equals 1 minus x squared minus y squared. From the same, if you just take the gradient, it will be the gradient of g will be minus 2xi minus 2yj, and you can have the reverse convolution here for the function g. So that means g xy, g function has absolute maximum value 1 at the critical point, which is the origin. So let's remind those graphs again. Function. So here, as you can see, the origin is the where the z function gets its absolute minimum value, and here for, if you define the graph on the right hand side, is gxy, which is 1 minus x squared minus y squared, and you can say 8.1, or you can, it is better to say let's say at origin, it gets its maximum, absolute maximum value, which is 1. Okay, so those are the functions that we have seen on the example. And here we have one more example. The function is y squared minus x squared. And again, if you get the gradient vector of h, and you can see that it is minus 2x I plus 2yj. And again, for this function, also the origin is critical point. But as you can see, at origin, h gets 0, so h0, 0 is 0, but hx0 is smaller than 0, right, for any x, because we have minus x squared here, and h0y is always positive, because y squared will be positive. Here you have minus x squared as the value of hx0, so it will be always negative. And here h0y is equal to y squared, so it will be always positive. So near origin, those are the points near origin, x0 and 0y. And if you get close to origin, and if you take x and y here, which are values, those are close to origin, let's say, then that means you don't have any conclusion that we need to say, say for local maximum and local minimum value of hxy. So that means at critical point h has neither local maximum nor local minimum value. So that is why. Okay, now we will give another definition for concrete. What is classification of 0, 0? So this is our h function. So this is h at xy, which is y square minus x square, and a critical point of the domain of function of any f of several variables is called saddle point if it does not have a local maximum or minimum value. Birimizin mikrofonu açık kaldı arkadaşlar. So that is why for the example here you can see the origin is not local, also not minimum, local minimum or local maximum. So that is why here the origin, the point of the function y square minus x square. Bir mikrofon açık kaldı ama arkadaşlar bir baksanız bayağı yankı yapıyor bende şu anda. Saddle point'te anlaşılmayan bir şey var mı? Eğer noktası diye geçiyor Türkçesi. Sesim net geliyorsa bende bir cızırtı var ama inşallah net geliyordur. Tamam, sesle alakalı bir problem olursa yazarsınız, şimdi bir şey yazmış kimse. So here for this function h x y, which is y square minus x square, the origin here will be the saddle point. So as you can see, it is neither a local maximum nor a local minimum, because here if you just try to compare for the other values of the domain of h, x, y, for example, any value here will get a value less than h0, 0, and also let's just give as an example, any value that function gets here will be more than h0, 0, more than 0. So that is why we will call that critical point the point of the function. And another example, the function which is square root of x square plus y square has no critical points. So there is no point where the gradient is 0, but it has a singular point at 0, 0, where it has a local and absolute minimum value at 0. So where the gradient is not defined. It is at the point 0, 0, and this is where it has the absolute minimum value, which is of course f00, which is 0. And for another function here, which is 1 minus x, also defined for all points on xy plane, and it has no critical points and singular points, because if you compute the gradient of f, it is minus 1 times I. But if we restrict the domain of f of our function to the disk x squared plus y squared smaller or equal to 1, then for that restricted domain, f has absolute maximum and minimum value at the boundary points of the disk, so which is the on the circle x squared plus y squared equals 1, and the maximum value is 2, which is f minus 1, 0, and the minimum value will be 0, which is actually f1, 0. So let's try to see the graph of 1 minus s, example that we see now. So this is the plane 1 minus x. So normally it is defined for all xy points in r squared or in xy plane. So for that, without restricted domain, it will have no absolute maximum or minimum value. But if you just restrict the domain of 1 minus x on that closed disk, which is x squared plus y squared smaller or equal to 1, so you restrict the domain on x squared plus y squared smaller or equal to 1, then as you can see at point 1 minus 1, 0, the function 1 minus x gets its maximum value, which is from 1 minus 1, which is 2, and at point here 0, 0 at the origin, it gets its minimum value, which is 1 minus 0, so which is 1. So this is the restricted domain that I shaded by yellow here, and this is the graph where it shows the absolute maximum and minimum domain, and the graph here on the left hand side is the first example that we see. So at point 0, 0 at origin, the function square root of x squared plus y squared has its singular point and also gets its absolute minimum value, which will be 0. So these are the this is one method, let's say. The local external values, or actually let's say the n values. Now here we will have a method classify all critical points. So if AB is a critical point of our function and HK are small values, so that means those are close to 0, and if we consider delta F as FA plus H, B plus K minus FAB, and if delta F is greater than 0, then F has local minimum value at point AB, and if delta F is smaller than 0, then that means F has local maximum value at AB. If delta F is smaller than 0 for some HK arbitrarily near 0, and also it can be positive for other points, then we call AB is the saddle point of F. This is one method. Also we will have another method, the classification. Let's give an example to just see the application. Fxy, the function is 2x cubed minus 6xy plus 3y squared. First we need to find the gradient of f, so which is 6x squared minus 6y minus I plus minus 6x plus 6y squared times z. So the critical point is where the gradient is 0. So if you just solve the equations, then the critical points are those two points, which is 0, 0 and 1, 1. So first we will start by considering the critical point 0, 0, and we will compute delta f that we define above, which will be 2h squared minus 6h times k plus 3k squared. And since fh0 minus f00 is equal to 2h cubed, it is always positive for positive h that is close to 0, but it will be negative because of the power of h, of course, that happens, which is an odd number, which is 3. It will be smaller than 0 for negative values of h. So that means 0, 0, that critical point is a saddle point of the function. And to classify the other critical point, which is 1, 1, again we will compute delta f, which will be this time 3 times h minus x k squared plus h squared times 3 plus 2h. So for this consideration, absolute value of h is smaller than 3 over 2. If absolute value of h, sorry, smaller than 3 over 2, and where hk is 0, then that delta f is positive for small values of h and k. So that means f has a local minimum value at point 1, 1, so which will be just from the definition of fxy, which will be f11 that equals minus 1. So that will be local minimum value of the function. We generally use the test that we will call a second derivative test. it is much easier to conclude actually. So let AB is a critical point of our function, which is interior to the domain of f, and we will assume that also the second partial derivatives of our function are continuous in neighborhood of that critical point, and have the following values at that point, and where we call capital A as second derivative of f with respect to x at point AB, and we will call B as again the second derivative of f, which is f1 to AB and also f21 AB, and C will be equal to f2 to AB, the second derivative of f with respect to y at point AB. So for those assumptions where we define AB, if b square minus ac is smaller than 0, and if a is positive, then we will directly say f has a local minimum value at the critical point. If b square minus ac is smaller than 0 and a is again also negative, then f has a local maximum value at the critical point. And the last one, sorry, not last, if b square minus a square is positive, then f has a saddle point at AB at that critical point. And if the last one is if b square minus ac is equal to 0, then from that result you cannot say or you cannot classify that critical point, so the test does not work in that case. So if you have the last conclusion, so that means you should use another method to classify the critical point here. So generally it is confused by b square minus 4ac, which is the discriminant, so be careful that it is b square minus a times c. Okay, so this is what I want to remember. An easy and direct method to see the classification of any critical point. Let's say here the function x times y times e over minus x squared plus y squared over 2. Of course, they need the second derivatives, so we will start by computing the first partial derivatives of the function, so which are f1xy and f2xy, and after that for the second partials and also we need to derivatives one more time. So it is for f11xy, so if you differentiate f1xy one more time with respect to x, you will get f11xy, and again by differentiating this time f1xy with respect to y, you will get f1 to xy, and also if you differentiate f2xy one more time with respect to y, then you will get f2 to fxy, sorry, f2 to xy. So those are the second partial derivatives that we need to know. And let's, okay, So the discriminant gradient, sorry, so those are the components of the gradient vector of f, so which are f1 xy and f2 xy, and those two both 0 when xy is 0 0 1 1 1 minus 0, sorry, 1 minus 1, and also minus 1 1 and minus 1 minus 1. So those are the critical points where f1 and f2 are 0, or that means equivalently the gradient vector is 0. So of course we need to classify all these points by using the second derivative test. So you need to find f1100, so which will be A, f1200, which is B, and also f2200, which will be C. So after computing all these, we will compute b square minus AC. So for the critical point 0 0, it will be 1, which will be a positive value, and from the test, that means the critical point 0 0 is a saddle point of our function. So we already classified one of the critical points, which is the origin. And if we continue by the second one, which is 1 1, and also A, B, C are equal for the other critical point, which is minus 1 minus 1, we will compute f11 1 1 and also f11 minus 1 minus 1, and also A and C are, you can say, pure second partial derivatives of the function at those points. You can say briefly, which is minus, which of course after computation, which gets minus 2 over E, so which is, since E is a positive number, which is a negative number then, and B is the mixed second partial derivatives of the function at those two critical points, to which we get 0. Of course, you need to compute those on the above results. So here, okay, let's see B. This is the for 1 1, f1 to 1 1 will be B, right? So let's see just for this one, this critical point. So this will be 1 minus 1 square times 1 minus 1 square times E over minus 1 square plus 1 square over 2. So we don't need to compute that, because 1 minus 1 square will be it's 0, so you don't need to compute the rest. So you can see B is 0, right? And after that, you need to compute B square minus AC to apply the second test, so which will be minus 4 over E square. Again, E is a positive number, and that means B square minus AC here will be a negative number. And A is a negative number here. So from the theorem, F has local maximum value at those two critical points, which will be f11, and also this will be equal to f minus 1 minus 1, so this will be minus 1 over, sorry, 1 over E, which will be the local maximum value of the function. And the other critical points are 1 minus 1 and minus 1 1. So again, if you compute A, C, and B, you get that A is positive, B square minus A times C is negative. So which means, from the conclusion of the theorem, F has local minimum value at those critical points. So which will be F1 minus 1 and F minus 1, 1, which are equal to minus 1 over E. So any question for second derivative test for the classification of critical points of problem var mı arkadaşlar? İkinci türev testinde. Dediğim gibi biraz önce söyledim. Ama yine tekrar edelim. Genelde bu classification için, yani sınıflandırma için kritik noktalarını, fonksiyonları genelde bu ikinci türev testini kullanmak işimize geliyor. Öyle söyleyeyim, daha kolayımıza geliyor. Ama mesela burada C'nin sıfır olduğu durum. Bu durumda classification için, yani sınıflandırma için başka bir yukarıda gördüğümüz gibi, yaptığımız örneklerde yaptığımız gibi metotlar uygulamanız lazım. Bir kere x AC'nin sıfırdan farklı olduğu değerleri için her zaman bir sınıflandırma yapabiliyoruz. Burada gördüğünüz gibi 1, 2, 3'te olduğu gibi. Kare eksi AC şeyde çok karışıyor. Diskriminant B kare eksi 4 AC akılda o daha fazla olduğu için, bu ikinci türev testini ilk defa gördüğünüz için muhtemelen onunla karışıyor. Ona dikkat edin. Burada bir 4 çarpanı yok, fark ettiyseniz. B kare eksi AC aslında bu mixed partial dediğimiz, yani F1,2 ile F2,1'in bu kritik noktalardaki değeri tabii ki de olmak üzere karesi eksi neylerin çarpımı, pure partial'lar dediğim F ikinci türevi, pure mixed partial derivatives dediğim, second order partial derivative F1'larla F2 çarpımı. Bu kritik noktadaki tabii değerlerin çarpımı olacak şekilde. O yüzden bu B kare eksi AC olduğunu bir daha hatırlatayım. Dikkat edelim. Burada biraz daha zamanımız var. Ekstrem bu sefer distributed domainler üzerinde ekstrem değerler göstereceğiz. Şimdi burada aslında bir nevi bir tane burada bir örnek gördük. Okay. So we will continue by extra values of functions defined on restricted domains. And I guess this can be an example for this. But we will continue by the second chapter. So this can be an example because the function has domain as all xy plane, and we restrict the domain on the disk x square plus y square smaller equal to 1. Okay, so this can be an example for this. And let's see. Hypothesis here also for extra values. Okay, so first we will recall that the continuous function defined on, this is the condition that we had, a closed and bounded region in R square, because it is function of two variables, takes its absolute minimum and maximum value on that domain, right? So we said that on the previous chapter. If the function is continuous and defined on closed and bounded region, then it must have an absolute maximum and minimum value on that domain. And for this section, we will see how to find these absolute extra values for on, let's say, restricted domains, where the function fxy has a local or absolute extreme value at point AB in its domain, then AB is one of the following. Let's remind it again, where the critical point is, where the singular point is, and where the boundary point is. Also those theorem that one we have seen. And the theorem provides a useful method to find absolute extreme values. So which will be, first we will find all critical and singular points, and then we will find extreme values of f on boundary, and then we will compare the values that we get at the boundary points and at singular and critical points of the function. Then after that we can, by comparing all those values of f, and we will conclude what are the extreme values of the function. Let's see for the function x squared plus 2xy minus y squared, and we will try to find, of course, the absolute maximum and the minimum value of the function on the disk x squared plus y squared smaller or equal to 1. As you can see, normally the function that we have here, fxy, is defined on xy plane. So for any xy in r square, right? But we will restrict the domain here on the disk x squared plus y squared smaller or equal to 1. Let's say unit disk. We restrict it on the unit disk, and we know that the function x squared plus 2xy minus y squared is continuous on that unit disk, and f takes is, that means f has to have absolute extreme values. And first we will compute to find the critical points. We will compute the components of gradient vector of f, so which will be f1xy and f2xy, which are 2x plus 2y and 2x minus 2y respectively. So f has no singular point, but it has, so where there is no point where gradient vector is undefined, but it is 0, the gradient vector is 0, the vector is 0, where at point, or at the origin, at point 0, 0. So that means 0, 0, or the origin point of our function f. And now we will consider the boundary points of the restricted domain, which is the points on the circle. So the boundary of the unit disk is unit circle, which is x squared plus y squared equals 1. And it will be enough to find the absolute extreme values of f on the boundary points, and then comparing those with the value of f at critical point, which is the value of f at origin. And it is also here step that we will do is to parameterize the boundary whenever it is possible. So we can simply take the parameterization by letting x equals cosine t. So you try to let's say parameterize the boundary points, which is the points on the unit circle, x squared plus y squared equals 1. And how you can do that? For any point on that circle, you can write where t is in between 0 and 2 pi. You can just write the x coordinate of the points on the unit circle as cosine t, and also y coordinates as sine t. And we have, now we will again parameterize the function fxy in terms of t. So fxy will be, by that parameterization, it will be f cosine t and sine t. So if you just write the function in terms of t, which is our parameterization, it will be cosine squared t plus 2 cosine t times sine t minus sine squared t, because the function, if you remind the function, it is x squared plus 2xy minus y squared. So in terms of parameter t, it will be cosine 2t plus sine 2t. So now we are reduced to computing the absolute values of sine t, sine t, which we will call as one variable function now, as g of t. Okay. And after that, it is actually directly the same steps that we have seen for one variable. So the absolute maximum and minimum value on the boundaries will be, if you just compute the extreme values, will be square root of 2 and minus square root of 2. And since at critical point where f00 is equal to 0, we conclude that by comparing all those values, square root of 2 minus square root of 2 and 0, the absolute maximum and minimum value of fxy on that restricted domain unit disk, so which will be square root of 2 and minus square root of 2 respectively. So that will be, square root of 2 will be the absolute maximum value, and minus square root of 2 will be the smallest value here. As you can see, the absolute minimum value of f. So let's read. Will be to find first if you have singular and critical point of the function. Then after that, you have to parameterize the function in terms of t. Write t as a one variable function. So f as a one variable function, let's say, as gt. And after that, you try to find the absolute extreme values of gt, where now it is the one variable function. And also at the end, you need to compare all these values. You need to follow. So let's just try to read this example, and I guess we will continue for solution. So we will try to find again absolute extreme values of the function x times y plus x squared. on the restricted region, which is a triangular region. If you just shade, it will be a triangular region, which is given by -1 smaller or equal to x, smaller or equal to 1, x minus 1 smaller or equal to y, smaller or equal to minus x plus 1. So if we, again, we will have the same steps that we have seen on above example. By computing the gradient vector, we will need to find the singular points and critical points. As you can see, it has no singular points, but it has points. Then after that, we will find the boundary of that triangular region. So again, parameterize in a single variable, like that. We'll find the excellent values of g, and after that we will compare the values, and we will conclude by finding absolute excellent. Arkadaşlar, çünkü bu örnek bayağı bir uzun adımları. Yine aynı adımları inceliyoruz, yapıyoruz. Biraz önceki örnekte olduğu gibi. Burada yine aynı şekilde x7 üzerinde tanımlı bir fonksiyon var. X çarpı y artı x kare şeklinde. Ama ne yaptı? Yine aynı şekilde, yani normalde zaten kısıtlandırılmış bölgede mutlak maksimum, minimum baktığımız için buradaki kısıtlandırılmış bölgede, tanım kümesinin kısıtlandırıldığı yerde üçgensel bir bölge olacak. Buradaki şekilde tanımla. Bu kalsın. Çünkü dediğim gibi biraz uzun sürecek. Yetişmez şu an. Çarşamba günü burada 13.3'e devam ederiz. Example 2'den sonra.